Hi, I'm Stacy Diefendorfer. I'm a senior research scientist at VTRC, and today we're going to talk a little bit about what is BMD, or Balanced Mix Design. First off, VDOT is in the process of implementing Balanced Mix Design, and this is an example of our timeline. We've been working on Balanced Mix Design since 2018, and we've been doing research, we've been buying equipment, working with the industry to get trial sections out, and finally here in 2022, we're ready to start rolling out some preliminary implementation along with training. First, what is BMD? A good definition is offered by the Federal Highway Administration's Expert Task Group on Mixtures and Constructions in 2015. Asphalt mix design using performance tests on appropriately conditioned specimens that address multiple modes of distress, taking into consideration not only mix aging, but traffic, climate, and location within the pavement structure. The idea is to design a mix for the right location with the right materials. So why do we need to look at BMD? We want to improve our performance of our mixes so that we can achieve longer lasting pavement. Currently, we design using volumetric methods such as SuperPave, and even before that with Marshall mix design. The problem with these is that volumetric properties do not give us a direct indication of performance in the field. Additionally, the volumetric design cannot capture the impact of binder grade or special additives. We cannot account for RAP, RAS, or recycling agent in the performance. And it also requires significant assumptions when you're calculating volumetric parameters in mixtures containing recycled materials. So we think there has to be a better way. So AASHTO has come up with a specification that describes 4 approaches to using balanced mix design. You'll notice that 3 of these start with volumetric design. This is basically by plan. If you start with method A and work your way through method D, you will move from volumetric design with checking the performance properties of your mix to designing your mix to meet performance specifications. The first approach for balanced mix design, approach A, is volumetric design with performance verification. In this process, we start with our typical volumetric design. We're going to create our mixture, determine the optimum binder content, but then we're going to conduct performance tests, rutting tests and cracking tests typically. For Virginia, we're going to use the Asphalt Pavement Analyzer and the IDT-CT or Ideal CT cracking test. If your mix passes, you're also going to perform a moisture damage test, which we already do TSRs in state. You're going to check your Cantabro mass loss. And if all of these things pass, you're ready to establish that job mix. If any of these points fail, you will have to return and redesign the mix. This slide shows a detailed breakdown of how to do the volumetric design with performance verification step by step. Basically, it's all written out what was in the previous flowchart. Approach B, volumetric design with performance optimization, takes this a step further. We're now going to determine our initial binder content, check if we meet all of our volumetric constraints, and then we're going to conduct our performance testing. But instead of only conducting it at the optimum binder content, we're going to conduct it at several points around the optimum, similar to what we do when we're determining the optimum binder content for SuperPave. If the performance doesn't pass, we return and redesign the mix. If our performance passes, we're going to select our binder content, we're going to do a moisture test, and then we're going to move on to production. So it's baby steps. First we design, then we start choosing our optimum using performance. And again, this slide spells this out in more detail than the flowchart. The third approach is performance modified volumetric mix design. And again, you'll notice volumetrics are showing up here. Since we really don't have any other way to control a mix aside from volumetrics, we're never going to get completely away from that. For performance modified volumetric mix design, we're going to select an initial gradation and initial binder content. Notice there's no mention of volumetrics at this point. We're going to conduct performance tests and determine if this mix meets performance. If not, we go back to design. If it does, we can move on, select our optimum binder content, finalize our proportions, go to moisture damage testing, and move on to our JMF. So in this case, we're only going to worry about our volumetric properties at the end. We're going to measure those and make sure that they are reasonable after we've done the design to meet performance. And again, for those that like this written out in detail, here's additional details. Finally, approach D, performance mix design. In this case, we're going to do mix design without volumetric constraints. This is kind of the Wild West, and it's going to be interesting to see where we go from here. But you're going to be selecting your initial gradation, your initial binder grade. You're going to run performance tests at different binder contents, similar to the way we do for SuperPave. And you're going to determine your optimum binder content, your gradation, all of your component proportions based on performance only. That means no consideration of air voids, no consideration, technically speaking, of our VMA. All the constraints are off. However, as we all know, you can't go too wild. If your volumetrics are not going to be reasonable and rational, performance will never happen. So you still need to be aware of that. But once the idea with this is that once we have a design that meets all of these performance properties, the job mix formula is going to be solely based off of the volumetrics coming out of that mix. Instead of volumetric constraints creating the mix, we create the mix first and then determine our volumetric constraints after the fact. This is kind of the unknown for where performance mix design is going, but it has the potential to be very exciting as there's a lot of room for innovation. And again, more details for those who like to read. Currently, the balanced mix design state of practice, this is as of January of this past year, and this is from NAPA's information. The approach A, doing verification on volumetric mix designs. 5 states have specifications that are draft, provisional, or standard specifications. Illinois, Louisiana, Texas, and Virginia. 3 other states are using a modified volumetric design, approach C, California, Missouri, and Oklahoma. And 3 states have specifications that allow pure performance design, Alabama, Tennessee, and again, Virginia. As we move on, I'm sure we'll see this spread across the country, but it's kind of exciting to be out here in the first round. The type of mix types, the type of balanced mix designs that Virginia has in our specifications follow generally the approach A and approach D from the previous slides. In our specifications, however, we call them performance plus volumetric, or P plus V mixes. For those mixes, the design must meet all current volumetric and gradation requirements in Section 211, as well as performance testing requirements. So we're adding performance testing on top of our volumetric design. Performance-only mixes follow the approach D. They must meet the performance requirements. The volumetric and gradation requirements at this point in Section 211 are waived. Those may come back in the future, we do not know, but at this point, we waive the requirements in Section 211. However, once that mix design is established, the production tolerances from Section 211 are applied to the gradation and properties. So you can design a mix with whatever volumetrics you want, but when you go to production, you must be able to consistently produce that mix. Performance testing, the heart of balanced mix design. AASHTO MP 4620 is the new standard specification for balanced mix design. This specification basically goes through and offers all of the tests that have been most recently considered for use in balanced mix design. In addition to some of the tests, rutting, cracking, and moisture damage that are in this specification, we also specify a durability test in Virginia that we'll talk about as well in a minute. First off, rutting. When SuperPave came along, we seem to have solved our rutting issues to a large extent. As you know, cracking is probably our most pressing issue these days. For rutting evaluation, though, there are a number of tests. Fundamental tests like flow number and super pave shear tester, simulation type tests where we're actually simulating the action of a wheel on the pavement, and monotonic tests that basically apply a single load. For rutting tests, we have been using in Virginia the Asphalt Pavement Analyzer test since the early 2000s. We are continuing to use that as our design test for rutting. As we talk more about the tests and you hear more about the tests, this test is not sufficient for production. It takes entirely too long to get results. So we are also looking at some of the monotonic tests that we hope to implement in the future. The indirect tensile high temperature test and the ideal rut test. Neither of these tests has a standard available yet, but we anticipate that they will be coming out shortly in the next few years. The Asphalt Pavement Analyzer is used at 64 degrees C, our baseline binder grade for testing. The machine applies a wheel load to a pressurized hose that simulates the action of a tire rolling across the pavement. We measure rut depth after 8,000 cycles, and lower rut depth means increased rutting resistance. Pretty straightforward. It should be noted, though, this is an empirical test. There is not a distinct mechanistic relationship between the results of this test and the stresses and strains that happen in a real pavement. The relationships are statistical. Moving on to cracking tests. There are a lot of cracking tests out there. And to be honest, more continue to come out about every 6 months or so. You can see this whole list. I'm not going to go through all of these. You can feel free to pick up the AASHTO specification and it will give you more information. The test that we are using in Virginia is the indirect tensile asphalt cracking test. It's also called the ideal CT test or IDT CT test. There's a little bit of pushback on the use of the word ideal for obvious reasons, because it implies a lot of things that I don't think any test can live up to. So ASTM is pretty much calling it the IDT CT test. This test applies a static constant load to a specimen the same way as a TSR test. It's an indirect tensile test. We're going to apply a load and split the specimen. The test temperature is 25 degrees C, or approximately room temperature. We apply the load to failure and analyze the load versus displacement data. Very similar to the Marshall tests and nearly identical to TSR. Analysis provides a cracking test index or a CT index. The higher the index, the more crack resistant the mix is. Moisture damage is also addressed in balanced mix design. Virginia has been using AASHTO T283, the indirect tensile strength test or TSR test, for a long time. I don't know how long exactly. Probably somebody out there knows. And it's currently specified in section 21102H. The TSR value for Virginia is 80. And keep in mind, we also require, at this point, anti-strip in some form in every mix. So that is a kind of a double safety to make sure that we do not end up in situations with moisture damage. Finally, durability. The Cantabro test indicates the overall durability of a mixture. It's kind of a vague relationship if you think about what durability means. But in this test, what we're measuring is how much does a pill deteriorate when it is tumbled in an LA abrasion machine with no charges. We're going to measure the mass loss by measuring pills before and after testing and determine how much loss there is. The nice thing about this test is that it is performed on your gyratory pills, so you're not required to be making extra pills. It's pretty effective and efficient. The Cantabro test was originally used for porous friction courses. As it said, we're going to tumble the pills in an LA abrasion device at an average room temperature at 25 degrees C, and we calculate the mass loss. Of course, the less mass you lose, the better your durability. So Virginia's performance test criteria are pretty simply laid out in a table. You'll see the APA Rutting, Cantabro, and CT index tests, and the AASHTO or ASTM designations. the test temperatures, how many specimens are generally produced in order to perform the test, along with the required air voids, and the criteria. For APA rutting, we want the rutting to be less than or equal to 8 millimeters. For mass loss, we want it to be less than or equal to 7.5%, and the CT index must be greater than or equal to 70 for mixes. In addition, moisture susceptibility must be evaluated. That is not in here as a specific performance test criteria since we already have it in the specifications. One thing of note, when we're making lab-produced mix, say for design, loose mix must be aged prior to compacting. The Cantabro and APA require 2 hours of aging, typical volumetric aging for volumetric properties. The CT index requires 4 hours of aging because it is a performance test, and the AASHTO requires additional aging for mechanistic performance tests. So the whole point of this is balancing rutting and cracking. If we look at a graph such as this, rut depth versus CT index, remember an increase in rut depth, as is over to the right, makes your mix rut susceptible. Decreasing rut depths, of course, are rut resistant. As the CT index increases, your mix becomes more crack resistant. So our goal is to keep the mixes in the upper left-hand quadrant and keep them completely out of the lower right-hand. In some cases, for some situations, you may want a mix that is highly crack resistant, but you may not worry about the rutting. For example, if you need an extremely flexible surface for some reason that is crack resistant. Along the same lines, you may be able to handle a little bit of cracking, but you need something that is highly rut resistant. For example, in a rest area for trucks, where there is going to be significant loading. So mixes can be designed all over this place, but in general, we're aiming for the crack resistance and rut resistance, and we're trying to balance these. Because we know as we increase the rutting resistance of a mix, it becomes stiffer. And as stiffness increases, we move over to where we're more susceptible to cracking. The whole idea of balanced mix design is balancing these two phenomena so that we come out with the best performing mix possible. This gives an indication of how this can be done. These are some actual results from a couple of mixes that we've worked with over the last few years. You can see the blue mix with the diamonds. The first test was done at 5.6% asphalt content during design, and it was found to be lacking in the cracking. Instead of there are lots of things you can do to adjust a mix like this. You can add asphalt. If you add more binder, you'll see that the mix will move up and have better performance in cracking. The trick is to add enough binder to mitigate cracking without getting into the rutting zone. So this mix there at 6.1 asphalt content is about an 80 CT index and a rut depth of 6 millimeters. So we are reasonably close on the CT index, and we are well below the rut depth. We can also see what happens if we go a full percent in asphalt content. If you see the orange mix with the triangles, we had a test at 6% AC and one at 7. You can see at 7% AC, we have great cracking resistance, but that mix is going to rut. At 6%, we're in the green, so we know that it will both be rut resistant and more crack resistant. Certainly not as crack resistant as that 7%, but at the same time, we don't have to worry about it being highly susceptible to the rutting. And that wraps up the introduction to balanced mix design. Thank you very much, and if you have any further questions or concerns, please shoot me an email and I'll be happy to talk with you.